Hi everyone, and welcome to part two of why AI systems don't learn and what to do about it. So basically, current AI systems are quite rigid after they are trained, their weights are frozen, and you can't really learn from interactions with the world. So this paper tries to say, hey, what can we do about it? So let's take a look at what we have covered last week, a brief 5 minutes before we talk about what we're going to cover this week. So last week, we basically took inspiration from how kids learn. They learn by actions, they learn by observations. So basically, um, in traditional machine learning, we basically just train the model and you forget about it. So you do your fine tuning, data curation, everything. You don't learn as you go. But what we try to do is we try to steer towards autonomous machine learning, where you learn as you go. You learn from your observations and your actions. So there's this new system B here that we try to incorporate into the algorithm. So what is system A? System A is basically like similar to what we have done before in self-supervised learning. We learn a next token prediction. We learn the world model. We try to map what we see in the world to what we predict, and we try to match that prediction to what we see. All right. So this we do very well. Large language models do next token prediction. The best video models also do next frame prediction. JEPA does next latent space prediction. So all these are indicative of how powerful learning by observation is. But it's not enough. It's not enough to just do learning by observation. We also need to learn how to interact with the world, learn from our interactions, and that is what they call System B in this paper. So in System B, you basically learn from what you see, the reward you get if you are using reinforcement learning. You can use your System A to do some planning. You can use your system A, of course, to the world model to give you like reward prediction or like goal state prediction and so on. So, okay, so actually planning is not system A, planning is system B. So planning is basically you can use your world model, that the dynamics you have learned, and you can try to simulate the next few steps. Like maybe in chess, you simulate 15 moves ahead. Yep. So these are kind of things that you can do if you interact with the world, and then you use what you have learned from the observation to augment what you see in the world. All right. So both of them can work together, and you can see this combined diagram we talked about last week, where the trajectories are selected by system B because system B chooses the action. These trajectories can be learned by system A to get a better world model. This world model can then inform system B, and then you can do some prediction here. You can use system A for simulation, and you can also use system A, like because you have some prediction error to guide your attention, okay, to guide you to trajectories to explore more of the search space. Because if you predict wrongly, maybe you want to explore more. Like when kids learn by self-play, if they realize that, hey, how come this button doesn't lift to the flap being open, they are curious, they explore more. Or once they figure out that the button keeps making it open, they don't explore anymore. Yeah, so there's a study about rats and a liver. When you press the liver for the rats, the food come out, the rats stop pressing after a while. But if let's say there's a percentage chance, like 50% chance the pellet drops out, or no pellet drops out at all, they can spend their whole day pressing that lever. Real life example are humans in a casino pressing the slot machine. Yeah. So yeah, we kind of do this as well when we learn. So you can actually use system A and system B to help one another. And this is very, very important. So we stopped here last week. Yeah, we talked about also like goal-directed learning can be incorporated in System B. Yeah, for more info, you can refer to the video of last week. So I'm gonna talk about what we're gonna focus on this week. This week we're gonna do more about how we can integrate System A and System B together. So last week we talked about MuZero. MuZero learns an internal dynamics model, which means that given a current state, all right, you can try to predict what's your next state, all right, given your action. You kind of learn the dynamics G, all right, that enables you to predict what's going on in the next state of the world. All right. You also learn how to predict, like given the current state, you learn how to predict your next action. This is your policy. All right. And this is actually mapped to like a tree search look ahead. So you get more and more accurate at predicting the next action. All right. And so this is basically an example of how to use system A, which is like the world model here, to kind of guide this prediction. Because when you roll out, you are rolling out using the world model that you have learned, not the actual world model. So this is basically an example of system A helping system B to plan. And then once you plan with system B, what you learn from your policy, you can yeah, you can get a better policy. Yeah, so this is how MuZero works in general. So my gripe with MuZero is that they use loss functions to learn everything. And so this may not be that great because your loss functions can go in different directions. You may not learn very well. And also if you start with a wrong initial state, maybe you can't break free of that bad initial state. Yeah, I tried AlphaZero and I've encountered such problems, all right? So there's also another important element, which is H here, which is the abstraction network. Instead of predicting from the actual board state, you can abstract it into a more condensed form so that it's easier to do predictions on it. So this is like the latent state that Yann LeCun's JEPA talked about latent state. Actually, this is similar to JEPA because you predict in the latent state, where the dynamics model is in the latent state. All right. Um, any questions for this? This is just a recap of last week. All right. So this week, what we're going to do is we're going to talk more about another example of system A and system B, which is Dreamer. All right. After that, we're going to talk about models that integrate system A and system B together with a manager kind of module, a system M. And then we're going to talk about meta level optimization, like beyond that, and some group learning stuff like genetic algo and particle swarm optimization. So I think all these are quite important. The last part on group learning is not in the paper, but I think it's a very useful addition to do continual learning systems. So I'm going to talk about that as well. Right, so without further ado, let's talk about Dreamer. So what is Dreamer? Okay, Dreamer is actually quite similar to what you see in the MuZero slides. You also have a latent state. So this Z here is a latent state. They actually use a discrete latent states where basically you you actually have like one hot encoding for each vector here. And they realize that this works better than having like multiple numbers for each vector in the latent space. And this is an improvement. This is actually Dreamer v3. In the earlier version, the latent space is just a vector space, but after that they changed to like this kind of one hot encoding discrete. They call it discrete latent space, I believe. And this turned out to work better because it's, I think, more condensed. All right, so basically you create a world model and you predict, given this is the H is your latent space and this is your discrete latent space. You try to like map to one another. So using your latent space, you try to predict the next latent space given the action. And so this is what you learn based on the world model. You learn how to predict a latent space. And this latent space, interestingly, you can also decode it back to the world state. So like in Yann LeCun's JEPA model, when you predict the latent space, you can't really decode it back easily. Although, you can train a decoder, but you may not get it back. But, you can also train this decoder here to try to visualize what the latent space is. So this is world model on the latent space. So very similar to JEPA, right? Very similar, right? So you learn a world model, that's a system A learning because you learn by observations of your state space, and in this case, the action space as well, because you want to know how the action influences the next output. I mean, if you want to see other examples of this kind of latent space learning, you can check out, I think it's called Genie or something. This is by Google, I believe. The one that you can simulate games with the video. I think it's called Genie. I can't remember the name of the paper suddenly. Yeah, but do you remember that paper? The one that you can use the an image and then you just describe in words what you want and then the image becomes a video. Yeah. Okay. If not, I will stick with Genie. I think it's Genie. I'll go and check out the paper name again later. Okay, so you learn the world model. And then after that, you also learn like given each state, how good is the state value? So you learn this value here. You also learn how to predict the policy, which is the next section. Yes, someone speaking? Did someone talk just now? Okay, so basically, this is actor critic learning is more like a system B, like you choose what trajectory you want. And you have a system A also, which basically you learn the world model. Right? And then you can use actually this world model to also help to choose what you want here because you can simulate with the world model as well. Okay, so this is quite an interesting idea. So you learn multiple things here. You learn how to abstract your state space. You learn how to train your world model. You learn your state value. You learn how to predict your next action, your policy. You also learn how to get the next latent space, next abstraction space. So these two are similar because the world model and abstraction space, in this case, the world model is trying to predict the next abstraction space, as well as you know, you use the abstraction space to predict the next action. So very, very cool here because you can do so much here just by using your world model for predicting this. You can basically learn this without using the environment because you can just use your world model to do it. You can use your internal world model to do it. So yeah, this is all quite cool. But again, my gripe with this kind of learning is that everything is one big loss function, as you will see in this slide here. Everything is one big loss function, and the gradients can go in all different kind of directions for your dynamics, which is your world model, your prediction of your actions, which also can go in another direction from your world model representation. In fact, if you represent your world model differently, your actions might be different as well. So they can go in very different directions in the gradient updates when you do backpropagation. So this is something that I don't quite like. In fact, Dreamer takes like a few million iterations to learn. Yeah, it's very, very slow. Yeah, that might be the reason why also learning world models are not easy. Learning the representation again, if your representation of your state changes, your latent space changes, your prediction from using the latent space is going to be affected. Same thing for your dynamics as well. Okay, so you can see this is what they learn. They learn how to predict the next latent space given the previous latent space, given the Z, I believe is the discrete latent space, and then the action. Okay, then you also learn how to encode the one hot encoder, the Z, given your the latent space and the input X. Input is the image input. So in pixel space, I believe. Okay, so I mean, you can look at the X here. Yeah, X is the pixel space. Okay, so you also learn how to do the dynamics, which is like how to predict the next the distribution of your. Okay, this is a bit complicated because like this ZT hat is like more of a, I believe it's the distribution of your potential states. Yeah, I guess it's like you don't get, it's not like you do the action and then you straight away get one outcome. You can get a distribution of outcomes. Okay, so all these things here is basically some equations to say that, hey, what's my reward? Whether I should continue with the trajectory or should I end there? And how can I decode back my pixel space given, um, given my latent space? Yeah. So these equations here basically are just describing like how do I do my world model, how do I do my actor critic, and so on. Okay, I'm not going to touch too much into them because the key idea is this slide here. You learn the world model, you learn the prediction of your next state, and then you use both together. So this is an example of how you can learn from observation and how you can learn from actions, and you can combine both together. Very, very powerful. They achieve like state-of-the-art performance for like doing getting a diamond pickaxe and so on. Although just using world models alone is not as good as you know uh, like using some memory methods to learn from their memory state and start from the last memory. I think you can look at Jarvis one for Minecraft. They use a multimodal image text memory, and I believe it does better than Dreamer. All right, so there's a limit to world models because like you can roll out the trajectory of your world model, but it's going to be very, very murky after a while. Let me show you. Okay, so this is the input here, and they also give it like some context, like the context of where they are, and this is the input. And what you want to do is you want to do the next few frame predictions. So you can see this is the true prediction. From the wall, it goes here, then it goes here. And as you can see, the world model itself, okay, you give it the context and you give it the input. It looks a little blurry. I suspect this means that this is done in the latent space. Yeah, so if you recover from the latent space, you don't get the full like resolution of your pixels. I mean, this is not stable diffusion. I mean, even stable diffusion, you may not get back the accurate pixel representation. So you can see after like 20 frames, the image kind of looks different already, right, from the original one. So you can see that after you continue going through like the various actions, like you can see that there's discrepancies already. Like after the 20th frame, your world model doesn't gel anymore with your true environment. Okay. you might say yes, that's a disadvantage. But to be honest, humans also don't predict our world model that well. Like, can you look ahead 2 minutes into your future and predict exactly what will happen in your life? I don't think so. Yeah, so maybe predicting 10 to 15 frames might be enough already. Yeah, in fact, this is quite close. This prediction is already quite close already to the ground truth. Uh, yeah, in the MuZero environment, I believe this is MuZero. Yeah, this one over here, if you look at the robot, looks pretty similar. Yeah, so you see the robot environment looks very, very close, even up to 45. So you can see this is one thing about world models. World models, you can learn it very well if the environment is simple, but harder if environment is complex. Okay, this is again quite common sense, but I just want to put it here because like all this talk about learning world models is a tricky thing to learn world models. I've tried to learn world models before on a maze environment. And to be honest, learning the world model took a while. In the maze is easier because you move up, you go up the x the y coordinate, and then you move right, you go up the x coordinate. So you only need to learn up, down, left, right. Took about 100 iterations. Yeah, if you want to learn all this image thing, because you still need to abstract it, and take note the abstraction space is learned jointly with the dynamics, right? So this poses a problem. Okay, I believe in Dreamer v4, the abstraction, they use a more rule-based method to do it, if I recall correctly. So I think this learning of the abstraction space is quite important. And if you learn it jointly with your world model prediction, it can lead to gradient misdirections, like two opposing gradient directions you may not learn very well. I still think the abstraction space might be inbuilt and you just learn the abstraction space based on some inbuilt rules. I think that might be better. I mean, for humans also, like you might think that we can learn everything, but we do have inbuilt rules as well in terms of how we visualize stuff. We visualize the world in a 3D environment. If you look at some illusions about a mask, if the mask is put the other side, where you see the side of the mask that is like concave. I don't know. Okay, basically this is a face, right? If you turn the face opposite, you see a hollow shell, right? The mask illusion. Okay, you can search mask illusion, I think. The mask illusion is like once your mask is flipped the other side, you still see it as a face protruding towards yourself, right? So I do think that even human vision has already some inbuilt biases. We don't like exactly learn abstraction spaces based on observation. We have some inbuilt biases, and I think this needs to be encoded in the model. You can't just learn a general abstraction space. I think that's too difficult. Yeah. So of course, machine learning people, deep learning people say, you know what? I can learn everything with a loss function. Give me a loss function and I learn everything. Look at that. Give me a loss function and I learn everything. Sure, try it, try it. Yeah, I don't think this scales. Yeah. So I spent quite a bit of time talking about Dreamer because I think the idea is nice. The approach may be a little ambitious. All right. Okay, questions, comments before I move on to the next part? Yeah. You want to talk anything about Dreamer or you want to know about anything similar? Yeah. Derek?
One thing about the Dreamer paper, which I'm a little rusty on, it it just well, I don't know what the latest Dreamer uses, but the Dreamer papers that I read, it didn't use anything to do with transformer blocks, correct? They just did a basic
This is a
art.
CNN block. Yeah.
They
MLP
did
CNN.
basic, yeah, it's very basic.
I
It
think
was just a
Diffusion V4 they use diffusion transformers. I think they use transformers
oh,
in Dreamer V4. Yeah.
okay. I'll have to read the paper to see how the new transformer blocks work out. Because I like the architecture a lot, but I recalled reading about the architecture and seeing that the implementation was very simple. It was just very basic neural networks to make the training part easy.
Mm, yep.
So I'll have to read into that.
Yeah. To me, actually, the architecture is not, I mean, how you code the encoder, decoder is not too important. Like you can use a transformer block, MLP block, a multi-layer perception. You can use a CNN, convolutional neural networks. Anything goes as long as it can encode the right space. It can even be rule-based. You can look at this paper called Go Explore. I did some research on it where you basically have some memory, you store the memory and then you store the trajectory, and then go explore the abstraction space. It's just it's just grouping average pixel values together. Yeah. Yeah. So basically they take one big space and then I think they slice the image into 16 parts and then they just take the average color of that part, and that's the abstraction space. Yeah, and that works because like the game itself, like just somehow, your state spaces don't, like the background changes as you walk. So, your if you just round down the pixels into like patches like this, it's already enough to encode what's going on. Although to the AI, it probably makes no sense because it's just 16 squares, but it's enough to encode the representation. Okay, I have to check again because it's been years since I last read this paper. But I'm just saying that, abstraction spaces, you can use any method to learn as long as it encodes a unique representation that you can use that latent space for valuable subsequent learning. And what I'm saying is that I think this abstraction space might need to be learned beforehand, before you do the entire algorithm of your learning by observation, learning by action. Yeah, if not, it might be too difficult to learn that space. Yeah.
Is there any,
Yeah.
go ahead.
Yeah, go ahead, Rob. Go ahead, Rob. You're good.
Just wondering, is there any limitations when it comes to like context?
Which context are you talking about? Yeah.
Like just like size limitations of window, like for learning, like does it ever peak out or no?
You
Like
mean
size,
Dreamer, is it?
yeah, Dreamer.
Yeah, I think the Dreamer itself, if you look at the paper, it doesn't really learn how to get the diamond pickaxe, like less than 20% success rate, if I remember correctly. So it doesn't learn the world model fully because, for a very, very long states, you can see already, like imagine this the Minecraft world. After a while, your your state space prediction is not good for your world model. So maybe you can do tasks in a mid horizon quite well, but if you want to do long horizon tasks, it can be quite bad.
Yeah, like the Arc
Yeah.
AGI 3 test is this. When you do the Arc AGI 3 test and you compete, it's very like hard, like very hard to do. It's similar like to how this works, to be honest.
They also do some world model in the test examples, right? Like, yeah, yeah, yeah. I do think it's very hard to learn world models. Yeah.
The longer it goes, right? Like the duration, it plays a massive effect. At the first bit, like at the very first start of the context, you're okay. But when you're 2 hours, 3 hours in, everything gets blurry. It doesn't get sharper. If that makes sense.
Yeah. In fact, Yan LeCun did some experiment on GANs before. He keeps using it in his videos. He says that, if you learn how to use GANs to predict the next state, GANs is the generative adversarial networks. After a while, it gets blurry. Yeah, and that's because, in the real world, like let's give the example he always gives. Let's say you have a pencil and the pencil drops. Okay, you don't know where the pencil drops. The pencil can drop here, the pencil can drop the other side. And so at state one, at state zero, maybe the pencil is like that. At state one, because the pencil can drop in all directions, so the pencil might become like a superposition of pencils. Because like you have to predict not just for your one action, like sometimes the world can give you different actions. So your state one prediction might already be quite blurry already. Then when you go to state 100, maybe it will become like just one mass of pencils. Like, yeah. So I don't know how to draw this for you, but you can imagine that it's very difficult to do a world model when you have probabilistic outcomes. Like when you take a certain action, you may not get the same state all the time. Like for example, poker, you make a bet. Sometimes you win, sometimes you lose, depending on how other people react. The real world as well, you have multiple actors, sometimes factors beyond your control that you have no input about. Like sometimes you walk into like maybe as is no not say walk. For example, you choose a box, right? One box A or box B, one contains the price, one doesn't. And actually you have no idea which one contains the price because no information has been given to you. So you have a 50% chance maybe that you get the price, 50% chance you don't. But in your world model, you have to model both states because you experience both equally. And so you have a very blurry world model. So
It's really
yeah.
it's really interesting because you have to offload the context window somewhere else. You cannot rely on the context window in the model. It actually has to be offloaded to another source. because the more it goes, right, the more blurry it's going to get. So if you can prune the model's basically memory at that point, you'll still continue to have it sharper. Like it'll be less.
Yes, yes, correct. That's why stuff like Jarvis One and Go Explore, they actually store the okay, I can say multimodal memory. They store multimodal memory, and you're unable to reenact the trajectory from that point again. So like Go Explore, the name is basically you go to a particular state you like, and then you explore further. So essentially it avoids like this blurry prediction, because when you go, you can maybe go to state 100 and go state 100, maybe the state 100 is exactly this pencil here. And you can start off at this state and then you explore further. Yeah. So you go to this state and then you explore. So you bypass the blurriness because you only choose one particular state and then you explore from there. Yeah. So that might be one solution to, you just have to focus on a few good states and you explore from there. So like even in chess, the best algorithm, like for example, Stockfish, it uses some form of tree search. Okay, and the tree search, you have to start from certain points. Yeah. So you choose which points to go to by like previous values of the of good states. Yeah, you basically choose the states based on some preferential value selection and you prioritize your search over there. Yeah. So like alpha beta pruning or like Monte Carlo tree search uses this kind of idea. You don't search every possible state equally. You prioritize. So something like that might actually help to solve like the blurriness problem, because you just focus on a few key points of the future and you work from there. Yeah. Does that make sense? Uh,
No, I see both your points about the grounding and the memory, or at least the starting point based on previous states, whether it be memory or some other system. Because like even if you implement a different architecture or a different neural network block, like a transformer or attention mechanism, you get richer feature representations, but or better abstracted spaces, but you'll still run into the same issue of long-term explosion of predictive outcomes, where you kind of like have more and more trees exploding outwards over the different time steps of prediction. You'll still run into the same issue without full grounding. You're just going purely off of the internal model or the internal representation space. So
yeah.
I do kind of see the point.
Yeah. To me, I think a world model is still important because you kind of still want to predict what might happen in the future. But there needs to be other things as well to help to ground it better. Maybe your world model, you don't predict so far, and maybe instead of doing prediction in this kind of space, because like this is very long horizon pixel space. Like your world model could be in a more abstract space. Like maybe your world model could be like move forward, then you go to kitchen, like move left, put pan on stove. Then your world model could be like add the stove to the object, add pan to the object stove. Yeah. So something like this, like if you can, this is what was done in classical ProFi systems, where you basically have a more discrete representation of spaces. Like it's very rule based, and this actually can help to like ground your model better if you already know what the discrete spaces are going to be. Like one famous example is Text World. Text World is a RPG like game where you input text, inputs like move forward, pick up pen, that kind of thing. And then one of the best solutions is that you store them in some form of a um, tree space, like a knowledge graph kind of space. And using that, you can ground your further actions. And it's very, very discrete and reliable space because it's forever accurate. So this is a very simple example, but this shows that if you could do a very, very rule-based representation, maybe that's good enough. Like you don't have to predict everything in the pixel space. And this is what Yen LeCun says as well. Like when you drive your car on the road, okay, do you predict the movement of the tree leaves when you drive your car? Or it's not that important, right? Like unless the leaf drops down in front of you and you need to evade, otherwise what you actually need to predict is the movement of the other cars, and that's about it. Maybe
I
predict
would
who. Yeah.
I would argue though that everything is rule based in a world model because if you think about it, every time you do a maze or any type of, let's say, an objective, right? It's to complete a maze, a very simple task. But for a model, it's not as easy as for us, you and I. We can figure that out quickly. Now, when you're trying to go, let's say the context window is very, very large, right? We can use, and it's never seen it before, it's constantly changing, right? The role model's job is to basically, in theory, right, help from basically seeing the unknowns or seeing the knowns, and the other one's, so you need like two. You need one that understands unknowns and one that understands the known. So what do I look for? Right? What am I missing? And that's the rules. Because in the game of like driving a car, you're looking for other cars on the road, right? But you're also trying to drive on the road to make sure you get from A to B.
Mhm.
You know what I mean? So I would say everything is rule based and everything can just be gamified. And that's will get you your results faster if you're going to apply some type of real world system.
Yeah, definitely. If you already have the rules to your game, then you can create a world model much more easily than trying to abstract it from pixel space. Yeah, it's a very difficult problem to abstract this kind of representations from just the input pixels. I agree with you.
Yeah, the point of models like Dreamer and the Jarvis, the other Minecraft models, is exploring spaces with less obvious rules or without previously encoded rules, right? Like with chess, the reason chess blew up easily in the 90s and 80s with um, the chess engine that fought
Stockfish.
Kasparov. Yeah, that one. I always forget. Is because chess is a very codified game. It already has the grammatical rules pre-encoded in its board game. It's all deterministic. There is no fuzzy logic in chess. Everything is already encoded in the game. So you can easily feed that into a rule-based symbolic uh, engine and pre-code all of its Monte Carlo tree search based on symbolic programming. That's very easy to do, or at least it is to do nowadays. The issue is the point of training these neural networks is getting them to learn unknown environments where we don't already have mathematical models encoded for them or discovered for them. The point is to get the neural network to simulate or to abstract the best mathematical representation of the environment for a useful task such as prediction and problem solving. Um, but the main thing of trying to solve the issue is figuring out how best to represent that. So, or finding what best to encode and what best to let the model learn. And I think that's the golden question that researchers
Yes,
keep
yes. It's,
discussing.
it's what
What
you're
do we
born with,
encode?
nature versus nurture, right? Like what are you born with and what do you learn?
Yeah,
Yeah. The key word though is prediction because if you think about it, Stockfish cannot predict its next move. It has to run a bazillion variables, right? On every time it sees the chess piece at the time. It cannot actually predict anything. So when we're talking about like deterministic, you still have to have, that level of prediction. And that's where it becomes like really interesting because the learning mechanism is not based on the past or the future. It's based on the unknown, right? So our the question is how do you define the outcome? Like how do you find the goal, right? Because without that, it's like the self discovery part is what like predicting the next move, predicting what. That's the hardest part, like
yeah.
learning that aspect.
Well, I think I really like this paper. It covers like the meta agent or the meta system, and I think for humans it's the same thing where we already have pre-evolved or pre-developed parts of our brain for certain algorithms or certain representations or features or algorithms in our mind. And we have like essentially you call it like an emergent consciousness, and that is our meta control system that controls our attention mechanism and our focus mechanisms, um, and reroutes energy to what systems need to be used and what systems are not in use. And I do think LeCun and his team did that exact same thing here in System M, where yeah, exactly, metacognition, where your System M, your meta control system, does exactly that, the same thing a human consciousness does, which is controlling data control and data streams and prioritizing which ones to use, which ones to push back on in order to optimize whatever task it's either learning or problem solving. I think that's really what LeCun tries to get at here
The,
with his.
the question is, Derek, is this a architectural issue or is this a model issue?
Yeah, we probably wouldn't know unless we try it out because the model can have
That is
limitations, the architecture can have limitations. Right? It could be either. Yeah.
that is a research question.
Yeah. So anyway, I would like to, since we talk about System M, let's move on because in the interest of time, we still have quite a few slides to cover. So as what Derek has beautifully pointed out, System M is the orchestrator of System A and System B. So you learn from observations, you learn from actions. You learn the world model maybe in System A. You learn the trajectory selection based on a policy that you like in System B. They work together. But that's if you just leave them both to be like, what if they have different ideas? Like maybe System B will say, hey, I need to explore more of the left path, while System A says, based on the past few tries, maybe the right path is better. Yeah, but they might have some conflict, and they cannot resolve it by themselves because like who is to be prioritized, right? So you can have a meta control where you take into account like what each of the systems give as input. And then maybe you also have another memory module where you can see like in the past what works well, what didn't work so well, and based on that, like the three of them in the paper, they didn't talk much about memory, but the memory is very important. As you see in the earlier papers that I talked about, Jarvis 1 and Go Explore, they can outperform algorithms just because of that the memory module that they have is so powerful. And in LM systems, those with a memory module, like you can update your context. The reason why Anthropic is so good is their context is continually updated and summarized. Google has a paper talking about context summary as well. The memory is so important. Okay, and using this memory, you can then see that, hey, maybe this trajectory is better because in the past is good. So maybe I should go with that. So yes, system B, you can go ahead. Yeah. So this system M can say, hey, yes, I'm going to go ahead with your trajectory. Okay. You can be frozen here. Okay. And then system A, you better learn from this trajectory. You go and learn now. All right. So then as you encounter the next few states in the world and then you realize, hey, how come I went to the left path? It's supposed to be good, but I have no reward there. Then you have to question yourself, is what I learned in my memory accurate? Is the world already gone? I mean, is the world already changed? Then maybe I would say that, oh yes, maybe I need to change. I don't freeze my memory, I'll overwrite my previous memory, and then I will learn better. So this memory, I treat it as a non-neural network fast retrieval. Okay, because you can retrieve states very fast. These two are usually neural networks and slow. Okay, okay, not fast retrieval, sorry, slow learning. This non-neural network part is a fast learning because you can just update the weights very, very quickly. Yeah, you can look at my paper, Learning Fast and Slow as well. I talk about these two systems where you have a system where it's very, very fast to change the information because it's like a database. It's like the episodic memory or some kind of memory. And you have a system that is very slow to learn because you need to update the weights. But when it comes to retrieval, okay, the system A, system B kind of neural networks are retrieve very fast because it's just like a one pass of the neural network. While your memory might need to go through your memory one by one, the memory might link to one another. It might take a while to get the memory, so it's a bit slower to retrieve. Okay, but both of them are important because when you have one of them, when the environment changes, in order to learn fast, you better update your episodic memory first before your system A and system B can change. Because system A and system B takes quite some time to learn. You know, you have done neural networks before, you know it takes hundreds of thousands of iterations to learn something. Maybe simpler environments, thousands. Yeah, but episodic memory you learn in one instance. Right. So you can use this to kind of decide what to learn. And then yeah, this so basically you have this system M that decides who should be learning, who should be inferencing. Inferencing, I treat it as a frozen. Basically, you don't change the architecture anymore. So you need some form of orchestrator to tell you who should go and learn. Okay, system A, you better correct yourself. You are wrong. Go and change, right? Or you can tell your episodic memory like, hey, you probably should update your memory. It's not accurate anymore. Yep. So this is what we call like how do we learn from data streams. So you can see that um we have data streams, and then you can actually learn the sensory inputs, motor commands, latent representations. Yeah. So this choosing of what data streams to learn is the job of the meta control policy. And you can see this is what they do. Connect data from a certain source to another source, change the mode. Okay, basically, should I change my system, basically change the memory or change the system A and B, or should I just use it to inform the other systems? And I also can say that, hey, you know, system A, you need to change your world model, okay, because it's not similar to what we see in the world. Okay, so this guy is quite important. This system M, because yes, has a lot of things to do. You need to manage the different inputs it receives, and it needs to tell the input sources. You need to learn. Okay, or you are right, you're wrong. So it's quite difficult to do because in order to do this, you need to balance your inputs. How do you know which input source is correct? Right? What if even this world input, sometimes your world input you might treat it as ground truth, but what if you know you are like in a certain place where you misinterpret the world? I don't know, maybe you think that you are walking in a grass plane, but actually you are in a VR simulation and so on. Yeah, so this part might be wrong also. So it's quite difficult to juggle which is the source of ground truth. Okay, of course, you give priority to the world, right? Like this is a prioritized for ground truth. But you know what if this part is wrong also? So so this system needs to be able to discern like what needs to change, what doesn't need to change. And this system is called system M. And unfortunately, there's no real like no real true system of system M being built. It's just a concept. The paper did give several examples of system M. Like for example, you can use some methods like prioritize experience replay to select trajectories to learn. I don't really like prioritize experience replay actually because you still store a lot of like you're still learning from trajectories. It's just you select, you don't really learn. I still think you need to learn from goal directed trajectories. Like what I talked about in my learning fast and slow paper, you given a start state and a goal state, you learn the action. Yeah, I think that's still the best way of learning because you learn from like failed trajectories or successful trajectories. The paper also gave another example. It's called hindsight experience replay. So basically, it's very similar to the goal directed thing I'm talking about. Like make any end state a goal, make any intermediate state a goal, and learn from it. Yeah. So this is more in line of the spirit of the paper that I did. It's more in line with this spirit. Although this only talks about end states, in this learning fast and slow, I also think that the starting state can be shifted. So you can learn from any starting state, any goal state. Very, very general. So these are some examples of system M. I think this is something that people should implement because we kind of need this for continual learning. Can you imagine all the components of system M being frozen? The memory is frozen, system A is frozen, system B is frozen. Like okay, this world interaction, we don't talk about it because we can't change too much about your body, right? You can't change, suddenly grow an extra arm or something, right? You can't do this. So we treat this as fixed. Like if you have everything fixed here, can you imagine that this agent is going to be very, very like rigid. Okay, it won't really learn from what it sees. It'll just learn a fix. It will just produce a fixed algorithm. And this kind of agent is known as a ChatGPT or LM. You have everything frozen already, so you don't really learn as you go. Okay, maybe the saving grace is you can search the web, you get more information. Yeah. So I think this is something that needs to be incorporated if you want a continual learning agent. You will need to change the episodic memory, change the system A or system B, according to what is defined as good by system M. Okay, so I'm going to pause here for a while. Any questions or comments or discussion? Yeah, it can be anything. Okay, so I think it's clear, right? This system M. Yeah, this is a very high level system. We haven't reached this in AI yet because in order to do this, you need to know how to select your data streams to learn. And that's a difficult question altogether. Right now, humans select the data. Like we say that, oh, maybe we should train on this benchmark, train on that benchmark. What if the AI can select the data that it trains on? Huh? Think about it. Yeah. All right. So the paper goes on beyond the system M. So I mean, I actually thought system M is already quite high level already, but the paper goes on to say that you know what? We could have a meta system M. We could have another layer above system M. So it's like it's like we are saying that quantum mechanics is really difficult, and then it's like they are saying what if something is beyond quantum mechanics and yeah, mind blown, that kind of thing. Yeah. So this is what the paper is trying to do. It's trying to say that what if system M can evolve? Right? Think about it. System A and system B can evolve here, right? Because you have a system M to control it. What if system M can evolve because you have a architect? I mean, I call it the architect. Like if you look at the matrix, what if you can evolve because someone can change it? All right. So this is the next level, and this is what they call meta loop. All right. So basically, you start off like they use an evolution example, like maybe the organism can be starting off as a fish, and then it optimizes for the environment, and over time, the architect will change A, B, and M, and through the environment itself. At the end of the environment, you have a train A star, B star, and M. All right. This is what you reach at the end of a life cycle. And then the architect could see what's the loss that this has achieved. And then, in your next generation, maybe say, maybe I'll tune system A bit, give it a little bit of bias. Maybe the organism can survive better in the land. The fish needs to get out of land. Maybe I should give it bigger lungs. Yeah, that kind of thing. Yeah. So tweak it a bit. Over here, actually, there should be one more thing. If you really, really want to be precise, you need to tweak the body as well. Yeah, you can't just have the neural networks like your brain and like spiritual stuff. Like you can't really just use thinking itself to evolve. You still need a physical body because you're in the physical world. So they're missing one part here for the evolution, which is the body. All right. So the architect could be like, maybe I should give it better lungs. Or maybe, this is a predator, like I need to give it sharper vision so that the eagle can swoop down and catch the rat. All right. So the next cycle, it becomes an eagle, and then like, yeah, I think it's great. Maybe it needs a stronger beak, or maybe it evolves to the human pathway, then it becomes like, okay, I think maybe we need to have a more sturdy bone, after a while, then it becomes a human, like, or maybe we need to give it a higher developmental time so that it can become more adaptive. Yeah, so over time, your phi T, which controls your system A, B, and M, will evolve. And hopefully it gets a lower loss function here. This is the fitness of the organism for that cycle. And eventually over time, they say humans is the max. I mean, this is like humans are the epitome of evolution? Question mark? Actually, I don't think so. Like I think this is just one phase of it, but the image ends as a human. So this to understand how the meta loop works. Okay, yeah. Anything? Discussion?
Is this similar to survival of the fittest or no?
No, this is not survival of the fittest because this is still a loss function. Yeah. So if you can look at the next slide, um, at first I thought this was like evolutionary algorithm, right? It's not because what you do is you have the initial procedure, which is you initialize based on your meta parameters phi, you initialize your A, B, and M, and then through your update, which is basically through the system M, you update, okay, your A, B according to the environment, and then evolve over time, you get, as what I saw in the earlier diagram, at the end of the life cycle, you get A star and B star. Okay, and you get your A star, B star, and you you could give this um to the architect, all right? The architect could see, okay, what have you evolved over time? Like what have you over your last life, right? Your A and B evolve. How does it evolve? Okay, I don't know why they didn't put the M here because you can also evolve M, right? So this is a very weird equation because like they didn't put a lot of things in there. Yeah, so over time you can evolve these meta parameters phi again, and then you can initialize A, B, and M with this phi and do the next cycle and so on. So everything here seems to be a loss function, yeah, with one individual based on my understanding of this paper. So although it looks like it's maximizing the fitness of many individuals, actually it's just like using one loss function of a certain individual and maximizing it. Yeah, so this is my understanding of the meta loop. So I do think it could be expanded to do like kind of some form of group selection.
Would you say though that the component here is basically like, I don't know. So for an example, if I'm a 6 foot tall and I've got really good genetics, right? Or I'm a whatever, another person and I've got genetics, right? Is it genetics related or is it related more to like memory? Where would you say that this really lies?
There's not much memory here, you see, like there's no memory component in this up minimization, so it's just genetics. In this case, the genetics is like your system A and system B parameters. Yeah. Then
Okay.
based on the n parameters, the loss function you get from here, you optimize your initial phi that creates the A, B, and M. Yeah. So they don't really have the memory here. I mean, if you think of memory in the weights, then yeah, you could think of memory as in the neural network weights, then yes, there's memory. But if not, there's no memory. Okay, so this is basically my gripe about this. I think this idea of the meta loop informing system A and B is quite a nice idea. But unfortunately, everything is a loss function for them. So like I think this might be better off if we do multiple populations of people or multiple individuals. Maybe you have this still have a loss function, but in genetic algo, this got a fitness function. You still have some form of fitness function. You select the individuals for the next generation, and you do some crossover based on or mutation. You create some diversity, and yeah, basically over time, your individuals might become better and better, and you don't really need to like minimize this phi t, okay? Because like okay, maybe it's still minimized like that because genetic algo is still minimizing fitness, okay, but not purely for one individual. It is a level group level objective. Yeah. So as long as like one individual can hit that minimum, you take that individual and then you repopulate again. It's a bit different from okay, how I put it? Like this is an example. This is your loss. Okay, in a neural network loss, okay, we try to do gradient descent to the minima here. Right? This is what we try to do when we are doing gradient descent, right? But in genetic algo, you you might have multiple people going to different end results because and you don't have to like eliminate the lowest one. So like in gradient descent, maybe if your optima is not as good as another person's optima, you will just eliminate that person, eliminate that point. So this is gradient descent. one optima. Okay, but in genetic algo, you could have many optima because you can choose more than one person to survive to the next generation as long as it works. Like if you think about it, if let's say God, if there's a God like that selects organisms to survive, and they say that oh, only the fittest organism would survive, then you would likely end up with if only the fittest survives, then you won't have diversity. Okay, because you only have a certain organism surviving. Maybe the T-Rex survived, and that's it. There's only T-Rex in the world. Because in the next generation, if something evolved better, that something better will just replace the T-Rex, and only one organism will survive. Can you imagine how brittle the system is to continual learning? Imagine this gradient descent that you see on the left here. One day, the optima changes, the landscape of the loss changes. Okay, let me use a different color. The landscape of the loss suddenly changes to become this. Okay, can you imagine this thing is now here? It will have trouble adapting because maybe it will go here, it will go here. It will take many iterations to adapt. Okay, that's for neural networks. But can you see that if we were to do like genetic algo, if the loss suddenly changes and the loss changes to this, okay, I know it looks similar to what you've seen earlier, but you can see some individuals might be lucky and straight away survive, while some needs time to adapt. This is very much faster to
But
adapt.
how, sorry, sorry to interrupt, but the thing is, how does this work? Let's say, for an example, from a technical perspective, you have like multi-tenant or multi-use case or multi whatever you want to say it. Each time we have like a specialist, right? In like a category. You may be really, really good at soccer. You may be really, really good at something else. The idea is that over time, right, the best in the world get to the pros. So we do have some level of, and if you have, let's say, like multiple people in living in a world, right, they all have different skills. Not everyone has the exact same skill. Like, or you know what I mean, genetics in order to be the best, if that
Yeah,
makes
but you can
sense.
see that not only the best survive, you see. Those that are second best, third best, 100 best, they still live on and some populate the next generation. So we don't have a rule saying that if you are not the best at basketball, you die. No, no, it's not Squid Games here. Yeah. So if the world was like Squid Games, then you have very little diversity at the end. Yeah, but the rest still survive. So you still have diversity.
I don't think it's a big deal, honestly, because a lot of people have been looking at genetic algos because they think it's a cool direction. I don't think it's a big deal. I think they both have covered different strengths. I think gradient descent is best for optimization when you need to reach the maximum optimization via the minimum loss function. Regardless of diversity, you just need the absolute best version of that neural network, that model. And I think genetic algo is perfect for diversity when you need to do coverall solutions for more complex and dynamic environments, possibly, where there's a lot more nuance involved. So you need a genetic algo to be able to cover that diversity, be able to explore different paths that were not previously explored, because I would say it's not a gradient descent model. Now, gradient descent has a lot of optimizations like Atom and whatnot. Um, and it's gotten really good at getting past the false minimum issue, or what do they call it? The
Suboptimal, optima, or like stuck. Okay, I get what you mean. Basically, you stuck in a valley that's not the optima, right? Like,
yeah, false valley, yeah, false minimum, false valleys. I think genetic algo does a really good job of avoiding the false valley issue because you're covering multiple different populations and multiple possible solutions. So you're always going to find some minimum via multiple lottery tickets
yeah.
via the algorithm.
So this is a good point of discussion that I have in one of the discussion questions, but we can talk about it now. Is being optimal important or just sufficient? Is it or it's called satisfies or just satisfying things or satisfying are enough? So basically, if a solution can already get the job done, do you need to be optimal? Must we penalize those algorithms that don't Like, for example, if you are doing a navigation problem, do we penalize those individuals that don't take the shortest path and just kill them off straight away? Or, we can accept the diversity of solutions and let them live on to the next round. Yeah.
If there's one thing in life that no human can escape, and that's entropy, right? And if you think about the world of a real world model, and we think of physics, you have to take into consideration that there's always a difference of effort that has to be put onto some way in order to achieve a goal. And if you ask yourself that question, would you say being optimal solves effort? That's something that you have to, I don't know if optimal is the right word in order for
I
important.
I don't think optimality is pursued in most organisms in real life actually.
Yeah.
Like humans are definitely not optimal. Yeah, if we are, we will be like robots. We'll just be doing very, very similar actions and very rigid actions to do certain things. Like you walk in a certain way because it's the fastest, that kind of thing. But we don't do that. Yeah. We are definitely not optimal at all. Yeah.
But
Well,
there's something biomimicry, which is optimal, isn't it?
Biomimicry is also not optimal because you can mimic the wrong stuff,
Hmm.
right? There's a biomimicry where little chicks are hatched and then they just follow the first living organism they see. So like if it's the mother hen, they'll follow the mother hen. But if it's a human, they'll follow the human. So is that optimal? Maybe because most of the time the hen would be right beside the chick. But sometimes it can go wrong. But the thing is the chance of it going wrong is so low that the chicks still survive until today. Yeah.
one really good example of your analogy is actually the A-star algorithm, which we've talked about several times on other research papers. It's a very basic heuristic. It is not the optimal mathematical rule, but it is such a useful heuristic that covers almost all solutions most of the way well that it gets used by Google Maps and every other software company. A star algo. Yep. It gets used by like every pathfinding company, every map software. The A star algorithm is a perfect example of a general heuristic that gets applied and covers most solutions. It's not the optimal solution for every single use case. Same thing in nature, where genetically an organism over its population lifespan as it evolves over time will start to mimic certain heuristics or pick up on certain heuristics by evolution over time and pick up on certain things like camouflage or swarm intelligence, certain things are heuristics that prove to be extremely useful for its environment but are not fully optimized, right? Like I'm
Yeah.
like if you take an ant and you grind it to max perfection towards a specific goal, it will look very different from whatever its form. It's the point. The point is the genetic aspect allows for diversity. Diversity is important. So my overall point from earlier was that whether you're using gradient descent or genetic algo for your fitness or your optimization, whatever you want to call it, your objective is that they are both tools to be utilized. I don't think it's one or the other. I think it's knowing what to use and when and why, more importantly.
Right. Yeah, I do think a system can have both architectures of optimality and
Yeah.
just like natural selection, evolution, like for example, like you can use like some stuff like alpha evolve where you have some genetic algo version combined with like selection of individuals based on ranking score. Yeah. So I mean it's very similar to this. Actually, this is the same as genetic algo. It's the same thing. Yeah. It's just that alpha evolves uses neural networks to do the population. So I think this is something that like most deep learning researchers are they like deep learning researchers are too engrossed with optimizing loss function. Yeah.
Actually, now that you put it this way, though, the real definition of optimal, right? And this is really unique to say, but would actually be a swarm intelligence modeling after a beehive, not just one level of intelligence. Because if you think about it, a beehive is legitimate optimization at the highest level possible.
Correct. So that's a good segue into group learning. So I think this is not covered in the paper, but I do think that this is definitely needed in an adaptive AI system because this learns very fast, right? Learns very fast, and it's not just stuck to one optimal solution. It gives a diverse group of solutions. So what we talked about earlier, genetic algo. So I took this from some blog where they basically randomize the angle where the car would move next, left, right, and if the car collides with the road, it dies. All right. So after a while, the the car actually manages to learn the entire track, but it only learns this track because it doesn't sense the road. There's no vision. It's just basically moving left and right and see how far it survives. And the furthest one would repopulate again and it completes the track. So genetic algos have been used in many games because it's very simple algorithm. Like you just see who's fitter and then you do the next generation and so on. You can use genetic algo to create AI for tic-tac-toe, Connect Four, like if like those kind of games where like you puzzle games, yep, where you need to like swap, like Candy Crush, for example. Yep, you can use a genetic algo to do that as well. You can, yeah. So basically, there's many things that you can use genetic algo for, and it does it brilliantly because you can just repeat the same environment again, but this is for same environment, right? If you want to do genetic algo across like the environment keeps changing, your genes need to specify meta parameters that control the algorithm, right? But for same environment, genetic algo works very well as there is enough diversity. This is very important. Okay, because if there's not enough diversity, maybe the solution is only one narrow path, you might not reach that path. But luckily for most real life cases and in most games, there's no only one path. Like you must only choose one out of million actions each time step, then you will win. That doesn't really happen most of the time. So genetic algo still works, okay? Because you can still use a very simple algorithm and choose like a good action based on the algorithm, select the individuals and basically make those individuals become the next generation. So this is a visual by ChatGPT. I think this is an awesome visual. Like I gave it like full 5 stars out of 5 stars for this because I tried to find a visual for genetic algo online, but I couldn't find a nice one. I just asked ChatGPT to give me a nice visual illustration of genetic algo. It gave me this very nice. So suppose you have a few chromosomes of like 101100. This could encode like different traits. Maybe like if the first one maybe like how you move in a maze, left, right, left, left, right, and so on. So you execute the sequence of movements, see whether you reach the end of the maze. Okay, you see the fitness, how far it completes the maze. You choose those that completes the maze as your parents, do some crossover if needed. Okay, mutate a few genes, and then you keep doing over generations, and eventually you will have a few individuals that solve the maze. Okay, so better solutions are likely to survive, reproduce, and then these individuals can help to propel the search for the next level, next generation of solutions. So if you think about it, this is actually very similar to like Go Explore. You store a memory of a successful trajectory and explore from there. Okay, you may not think that this is like storing memory, but you see, genes are like memory. Okay, they tell you how to how to survive in the world. So if you select the right genes, it's like telling the organism like this is a good set of starting genes. Just follow this blueprint and you will at least guarantee yourself to live a while. Yep. So but you cannot just have the best trajectories just maintain all the time because you can't grow from there. So you need to perturb a bit, like maybe you mutate a bit of the gene here. Instead of going right, maybe I go left now. I try to explore something, see whether it works. If it doesn't, then don't worry, next generation you won't see it again. Yeah. But if it works, then it's like, hey, yeah, this new individual works. Yeah, maybe you should try to use it. Yeah. So this actually works very well for a lot of different problem types. And I think this is something that we need to explore a bit more because I do think having a group of populations exploring a search space is more efficient than just having one individual and using gradient descent to navigate that space. I think having multiple agents is something that we need to look into because it's so much more efficient, right? I mean, you can use gradient descent. After you mutate, you can use gradient descent to, optimize that individual again. My friend Kaysen is doing some evolutionary algorithms that does that. Use genetic algos at the start, and then after that, use gradient descent to optimize that individual. You can do a hybrid like that. But the idea is that you still need a population of agents. If not, you won't be able to have diversity, right? This genetic algo questions, because I have another algo I want to talk about. Then we have discussion. Like maybe you can pause here for 1 minute if you want to ask anything about genetic algos. Okay, so you can see in research now we have a lot of genetic algo coming out for LMs like Alpha Evolve. There are other stuff. Okay, I wouldn't say it's genetic algo, but like at least papers that use multiple agents that are primed with different personalities to try to solve things. Yeah, these are kind of things that help to explore more of the search space. All right, let's move on to the next one. Next is called particle swarm optimization, one of my favorite optimization methods that are inspired by bees moving in a beehive, like what Robert said earlier. All right, so what is particle swarm optimization? Like every single particle or bee has its own like memory, but collectively as a group, they also have a group memory, and together they optimize towards the space that the group thinks is best and what they think is best. And can see eventually a whole collection of individuals navigate to this highly efficient optima. This is the best. Okay, if you were to use gradient descent, good luck, right? I mean, like you might get stuck here, you might get stuck here. You can see some individuals are stuck here as well, but these are rare. Most of the group goes to the honey, where everyone goes to the lowest point on the lost landscape, right? This is what I think is missing in deep learning. Like we kind of focus too much on just having one solution. Like why not have it more? Like people have tried. I think in deep learning they try to do like mixture of experts as well. Like you try to have different kind of biases for each expert so that you explore different lost landscapes. Yeah, but that's not enough because like this mixture of experts is still one organism at the end. Like you kind of need to have multiple organisms like this. And it's best if they do some form of competition with one another. In fact, you can do particle swarm optimization plus genetic algo. All right. You can select those starting positions and then you repeat again. Yeah, so there's evolutionary add-ons to this as well. Yeah, it's quite interesting. You can look at the literature for this. Um, very cool algorithm, very old school, but still good, I think. So this is by flocking birds and schooling fish, also by bees as well. So you have each particle having a certain initial velocity, and then like you see how good the position is. Okay, each particle will record over its life cycle which position is the best for it. And then across all the swarm, you have a global best. There's a best position by the entire group. Okay, and then you update your velocity with your previous velocity, with the global velocity, the global best position, the personal best position. Then it's a conflict of interest. But typically you will prioritize global best more than your P best. I mean, you have different weights you can adjust. Yep. And eventually after you move, hopefully at the end of it, most people are at a group best. All right. So this is very, very cool because you have agents that share information, collectively move towards better solution, and you approach an optimum. And I mean, if you think about it, if you have multiple LM agents right now, and then maybe you share memory, because like you can put like your best trajectories in a common pool of memory, and then each agent can access it. It's very similar to this because like you have a global best, which is like in this case the memory. Maybe an agent could have individual memory and an agent could have a collective database of memory. And you could access both of them and you can steer the agent towards a global optimal. So in modern speak, having memory that is shared between agents could perform similar things to particle swarm optimization in the context space. I mean, it's not in the weights and bias space, but at least in the input context to the LM, you can do that. Yeah, very, very efficient because you don't get stuck to having only one agent's trajectory. You have many agents' trajectory. But one thing bad about LMs, I tried using LMs for exploration. LMs don't explore well. Okay. You can try yourself. You ask it, give me a random number from 1 to 100. and you see the answer. You just keep doing this prompt, all right? It's not an RNG generator, all right? LMs LMs are not an R. So if you just use LMs to explore based on the prompts, like prompting alone is not sufficient to let LMs explore. Just if you are wondering about this, I tried to do this before. You try the random number one, you realize that some numbers are more often output than other numbers based on the training set. And that's yeah, this is something that you just need extra structures to do it. And particle swarm optimization, you do exploit based on still have a optimal that you go to. It's quite efficient. Um, I think it works way better than just using LM agents with memory. Like
One, yeah,
yes, go
sorry.
ahead.
One of the things though that you have to take into consideration, especially with LLMs, and I have like firsthand experience in doing all of this, so I can say personally, if you have let's say like a fill in the blank questionnaire, right? So I went to the blank, right? And then we ate blank, whatever. The LLM, right, has to come up with its words, right, in order to basically fill in those blanks. What happens though is that when you have human sensitivity and baked, I'm going to call it guardrails into the model, right, at training, you will see how far it's off from the actual word that I wanted to use. Now, you cannot have swarm intelligence. You cannot have any intelligence until you solve that problem first, because you're not getting true. Like, you're just basically getting a machine that's probabilistic that just lies to you all the time. So this doesn't work in the real world of basic like of LLMs, like or of any AI. It works like maybe human life, right? Because I guess we don't have that sensitivity, but not in the LLM world with that baked into it, because it's constantly, unless you can change it at inference, which would be, that's what you have to do. You basically have to direct the model at inference in order not to follow those baked in guardrails, if that makes sense. Like, well, I know it makes sense, but hopefully that makes sense.
Sorry, can you repeat that again? You must not do something at inference, or what was that?
If inference, you have to remove guardrails that's been baked into it,
Mm.
or it will always fall back to its guardrails. So, like I said, if you fill in the blanks, you can take a model and you can see that its word, right, it will change its word, and its confidence from that word will be like almost sometimes 500 points off of what it actually wanted to use to fill in the blank. It's crazy. So probabilistic AI as a core does not work in swarm part. It's all just, it doesn't really work.
Yeah, I mean, you can input the memory and it can still based on its earlier memory. I mean, earlier biases, right? The
Well,
prompt may not change much.
it's creating more entropy, right? Because basically what it's doing is it's going over a whole bunch of baked in guardrails that it has to go through first before it can go to its natural swarm. See, when a bee goes, they do like something called the waddle or like that, right? And the idea is like, we're going to now try to convince other agents to go back, or what we call bees,
The
whatever.
waggle dance, right? Like, and then you see how long the dance is to indicate how sweet the honey is.
And it could be miles and miles away, but these things have to go back and be able to find that, and other bees have to trust them, right, to build this natural level of trust. But you can't have this like extreme sensitivity bias inside. So this particle swarm optimization is fantastic in theory, but it won't work with LLMs that are probabilistic, that have so much baked in. Like, it just,
Yeah,
you have
definitely.
to.
So as what Yen Lukun says, LMs are limited in their usefulness. Like I think it's good to do certain tasks that are very standard, but the moment you need to adapt and change the output of the LM to different tasks, it has difficulty. Unless you pre-train all the tasks, which is what coding agents do. We pre-train on lots of code. That's why it codes really well. But the moment you have some new code that it has never seen before, it may not work very well anymore. Yeah. So I think this is a fair point to make. And that is why I think now is a key time in the deep learning space, which has done so well in learning by observation. Self-supervised learning is handled so well in deep learning networks. But now we talk about like learning from actions, learning from the environment, and that is not handled very well by deep learning. So I think instead of doing architectures like MuZero and Dreamer, where everything is a neural network and you try to optimize all the neural networks, why not incorporate group learning into it? Like then you might be able to explore the world in a more diverse manner. Like if you look at the dreamer here, you see the world model is like not great here. But imagine if you have different agents viewing the world differently. Maybe they each learn different kinds of traits. Maybe one focus on the tower, one focus on this green wall. Essentially, if you have a combination of traits, a combination of inputs by different specialized agents, you might better composability of true input. Like you don't have to learn the whole state space. Each one could learn a different state space, and then they can kind of learn the entire thing by combining things together. Like for humans, we have a motion detector, color detector. What else? I don't know. I think that's more like, so you can like sort of, when you have a ball coming towards you, the ball can come towards you like that. This is a red ball, and the ball can come towards you like this. It's a blue ball. Essentially, like the number of representations that each agent needs to learn is less, because the trajectory agent doesn't need anything new, because the motion detected, because you already know that it's the same trajectory. So the color one, the color agent would already generalize across previous examples. So so although like the first and the second one might be different examples, but because you separate your color from your motion, you combine them together like a group input. So each agent is specialized here. Okay, maybe it has access to different sensors and so on. So this is one level of agents, which is like within the individual, you have multiple agents. You can do your some optimization with the different inner agents as well. You can also do it at the meta level, where you have populations of individuals that you do your optimization there as well. No problem. But what I'm saying is that by composing your input into different parts, you actually can learn from fewer examples. And of course, you will need to be able to live with having biases, because these agents are biased. They have certain ways of viewing the world. So I think bias is very important for learning. Okay, you cannot have a strictly truly general agent. You need to have some bias. So this is what I'm thinking of, like a composition of inner agents that are differently evolved, and you can learn from one another. You learn with fewer samples. And at the higher level, the population level, you also have different individuals, and they each learn from one another as well. Yep. So yeah, this is at least the system that I'm thinking of. Yeah, it should work much better than deep learning methods. Yeah. Yeah. Any questions? Any comments for this? Like, yeah. So two levels of agents. One is a inner compositionality, and then one is a group population learning. In fact, you can even go higher than that. You can also have population level learning. Yeah. So one is group learning, one is population learning. Yeah, I think the list goes on and on and on. You can have learning at all levels, as long as you have a way to evaluate how good a certain level is with a loss function or fitness function. Your evolutionary algorithms can go as high as you want. Yeah. So this is exactly what the meta paper tries to do. They have a system A, system B that learns within one, I would say, environment. Then you have system M that learns the meta environment. Then you have a meta system M that learns even higher. But unfortunately, in the meta paper, everything is a loss function. I think they miss out on something that could be even better suited for this kind of adaptive learning, which is group learning, like genetic algos, swarm learning. Yeah, I think that's what's missing in current AI systems right now. Yeah. Any inputs? Yeah, I think this is something that I want to focus on a bit, because I think this is the kind of research direction that is more interesting for me. Yeah.
With Moonshot, like he said that it was post-trained agents on swarm optimization. Do you know anything about that, or like why that was done? With like Kimmy, I'm guessing Kimmy 2.5.
No, actually, I haven't read the Kimi paper, but you want to fill me
Me,
in with the
I read
details?
that.
Yeah. I mean, Kimi is a great model. Yeah, it's just that it's not high priority in my radar to read fully. Yeah. But I mean, I'll go check it out later. Yeah. Do you have anything you want to share about the Kimi paper? Who was the one who brought it up? Is it Derek?
Sorry, I'm outside right now. I'll
Oh, sorry. Oh, no worries, no worries. Yeah. Yeah. If you're interested, we can definitely talk about Kimi next time. Yeah. If they use form optimization, we can analyze how they did it. Yeah. Okay, if not, we'll be moving on. So we spend the next 15 minutes. Okay, we'll drag a little, but let's talk about some questions. So, first question, does system A need actions to model the world? Do we need to know our internal actions to do a world model? Or can we do world model even for things that we cannot do? Okay, let's think about it, all right? Give you a very practical example. Can you imagine how it is like to be a bat? All right, think about it. Imagine that you know a bat uses sound to echolocate. Imagine you know the bat flaps its wings and sleeps upside down on the cave. Can we do a world model for a bat right now? Anyone? Okay, so oh yeah, Derek, please go ahead. Yeah.
No, I was just gonna say it's funny you bring up this question because it's something I don't know why, but it's something I catch myself pondering a lot when I'm daydreaming or I'm going for a walk. I it's like a thought experiment I do where I try to imagine the perspective of another animal. Sometimes it's a dog, sometimes it's an ant, sometimes it's a corvid, where I have pigeons outside my apartment. And it's kind of just like a thought experiment because I catch myself making a lot of assumptions about how a third party animal sees the world, right? Because they don't have the same brain matter that I do, which means they probably don't have the same level of consciousness I do. Not to say that they don't have their own awareness, but they're probably not gonna have the same processing that I do, which is also gonna imply that they're not gonna have the same um, thoughts or thoughts occur, or impulses occur to them that I do, or at the level that I do. So this question of system A needing actions to model the world is tricky. Like I think humans have a much better time inferring what other humans are processing. But I think when it's a system that's much farther removed from ourselves, such as another animal or possibly something very abstract like social interactions or economic interactions, right? Like you notice a lot of the time, people have a really hard time predicting and timing the market. A lot of people lose money on the market and the stock market because the market, while it is a representation of human uh, buying and selling social behavior, right? Like where one purchase affects another purchase, affects another sell, right? It all compounds. It's not inherently as intuitive as social behavior or human social interaction or behavior. It's not one to one. So you notice that a lot more people or economists have a much harder time predicting the stock market or other markets like that, like prediction markets, because it's not a one to one of social human interaction, right? It's a system that's much further removed from something that's much more closer to us or relatable, like a one to one human interaction. So I think the further we get from um, ourselves or the way we think and process, right? Like say like the disconnect to our environment, right? Where you spend the same amount of time in a certain place for a long while, you become very desensitized to it. But as soon as a variable changes, you have to spend a lot of time relearning it yourself and relearning your assumptions.
Mm.
So Learning, inferring the actions of others' trajectories, if it's not our own, I think has a lot to do with how close the other person's processing of their environment is to us, right? The further their processing is from us, or the further away their mental framework is from us, whether it be like biological or architectural, I think affects a lot of how close we can predict or map our trajectories to there and vice versa.
Yeah.
I think it's the point I'm trying to make.
Right. I think it's a great answer. So based on your answer, I come to the conclusion, which is also the conclusion I had earlier, is like actions are needed. Okay, because if you don't have the actions, you can't model the world. You see, there's so many variables that are going on in the world. If you don't say that I want to move forward, how do you know what your next visual input will be, right? You need to have some grounding, and actions are the grounding. In fact, actions are very important because in order to learn, you need to take an action. Like this is basically like we learn by movement, we learn by pressing buttons, we learn by like if you just observe a screen and then the things come in your head, like it's very hard to learn. It's not a basic form of learning. We have to use higher abstraction spaces to try to map actions to like imagine this one plus one, then you try to move the one to another one and becomes two. You have to use imaginary actions in your head to learn this kind of things. We are not like an LM where we learn like one plus one equals, then next token is what. Yeah, it's very difficult to do that. Like actually, I think the way our brain works is quite far from how LM works. Like we actually use more abstract representation and then try to map back into language. Yeah, not everything language and then try to predict the next word. Yeah. So this one I think in world models we kind of still need actions, like because you still need to ground your world model in like what comes next. And that's why it's very hard to imagine how it's like to be a bat because we don't know how it's like to echolocate. We don't know how it's like to fly. Maybe we can imagine flying because we can flap our hands like that. But it's very different. Yeah, you don't have the body sensation to map how it's like to fly. Yep. So it's very hard to model like a life of a bat. But okay, if you want to talk about other actions like other humans, you can like look at like athletes. They can learn from like the like swim strokes of other people, like because they can actually watch how it's done, or like boxing, they see how people react to the punches and so on. You can learn because we have something like the mimic neurons in our brain, like same as monkeys. You can actually try to mimic the actions of what other people do. Right? That's what babies do all the time. They mimic their parents or their friends, and if the friend does a very, very bad behavior, next day you see the or you just even the next minute you see the kid performing it. Yeah. So as a parent myself, it's very important to correct such bad behavior earlier. Okay, if not, they will just they like to mimic things. Like so, this is something that we have evolved to try to mimic others so that we can learn from their actions as well. You see, if you can mimic what they do, you can learn their trajectory. Okay. Yeah. So this mimic, maybe as a child you do it outwardly, but as an adult actually you can mimic without moving your body at all. Like people have done experiments where they try to let people practice like the gripping strength of the hand, but they tell one group of people, you just think about gripping your hand. You don't move your hand. And then the other group, they actually can move their hand. And then at the end, they see whose grip strength, given the start and the end of the experiment, how much has the grip strength increased? Is it simulation in your head or simulation with real hands? And they realize the improvement is the same. So you can actually improve just by thinking about moving your hand, right? So the next time you think that, oh, I need to like really, really do the action out in order to learn. No, we can actually learn by simulation. Our brains can simulate things and you can learn just as well. Yep. So like that's like playing the piano, right? You can learn on by pressing the piano keys, but you can also learn by simulation, just imagining how your fingers would move. Yep, that would work as well. So we
In
still need
sport,
action, yeah, but we may not carry it out. Yes, go ahead, Robert.
yeah. So in sports, there's something called like court smarts, right? Or awareness. So you need to know where to be at all times, right? Well, yeah, you can take action by playing the ball, but you still need to know the court. You need to know where to be, right, in order to be at the right place at the right time. So there's a concept that they call intelligence. It's when you can like I've been trying to do it like a while lately after speaking actually to you recently about observing your own thoughts, right? So the question is, can you reason with your own thoughts? Because I believe reasoning is more important than thinking like a bat. Because if you don't have the physics understanding of how to think like a bat, the constraints, you'll never be able to be like a bat or imagine how to be like a bat. You need to first understand the physics and the limitations of what a bat can actually do and how it operates before you can ever get inside it. So you need to reason with your thoughts before. Like when you play the piano, right? There's different, anybody can play, push the keys, but to actually get, the right composure, the right temper, like all of these different, components of music, like especially like composure, like you need to really think about what you're doing. You need to have that reasoning, not just the ability to take action.
Yeah, I think reasoning is a higher level order of thinking. Yep, that you can perhaps do a world model for reasoning, but I think that's not really world models. That's more of another system. Like by world models, I just mean like the state and actions, a bit more fundamental. But you can, again, as I said, anything abstract can be a world model as well. It's just an abstract world model. Yeah, you don't model the actual world itself. You model in the abstract space. Like maybe reasoning could be in that space. You model something higher level. You model how the reasoning would be given a certain state. Yeah, you can try the action could be the reasoning itself. Yeah, that's a world model as well. Yeah, so that's why I say like you can learn stuff from text on the screen, but you do some form of world model in your head that, if you see 1 plus 1, you try to add the numbers up. Yeah, that kind of world model is there as well, and that world model does not correspond. So the actions need not be real world actions. It could be actions in abstract space. As long as you can visualize that abstraction space in your head, you can perform the action. All right. So I think our world model, if you just look at humans, the world model we have is not just limited to the real world actions like your muscle contractions and so on. The actions can be simulated. Like it could be even not related to your body at all. The action could be like in a game world, you want to do a diamond pickaxe, you need to craft. So the action could be craft. There's no craft in the real world. I mean, okay, yes, you can craft in the real world, but let's use another video game example. Um, you are maybe Harry Potter and then you cast a spell, like I don't know what spell, like he likes to use the disarm spell. So like let's just talk about the disarm spell. I can't remember what's the name of it. Yeah, but basically if you use that spell, it is no relation in real life at all, but you can imagine um that action because like in abstract space you can say, yes, I do this action. Okay, again, Harry Potter may not be a good example because we can actually imagine using our hand to do that wand. But I can imagine even weirder actions. Like for example, if you are, I don't know, if you're a virus particle and you evolve to having water resistance. If you play the game Virus, a pandemic, I think, you can evolve your virus to destroy the world. Yeah, so you can even imagine yourself being a virus, taking these various evolutionary paths, because you have this abstraction space in your head that can abstract to those actions. Yeah, so the world model need not just be real world physical actions, as long as your actions and your state space are in the same abstraction space, you can create a world model for that. Yeah. So you can actually learn the world model of other people's actions or the actions of a bat, even without mapping to your own actions. You can just learn the world model of how they would move. Like given like they flap their wings, this after the bat flaps his wing, it move up. If the bat echolocates, you hear that sound. Your the state and their action space might be a non-egocentric one. You can just look at how they move and then you can infer what will happen to them given that they do certain actions. So I think you can learn different world models as long as the action and the state space are in the same abstraction space. So yeah, I know this is a very complicated answer, but yeah, there are different world models that we learn. Yeah, we learn egocentric ones and we also learn ones about the world. Okay, yeah, I think that was a complicated thing. Just sit that in your head and think about it. Yeah. So next question, we have system A, system B, and system M. We have many loss functions objectives. Can we still learn by backpropagation? Is it conflicting? My answer is yes, it will be conflicting. It will likely be conflicting. So I recommend like maybe learn abstraction first, then the world model or the policy. Okay, so maybe it can help with that, or use genetic algo, right? That may be more gentle on the gradients. Like you don't have to learn all the gradients at once. You can use your population to sort of explore the loss function space instead of using gradients, right? So that's anything to add? Because I think we talked about this just now. Okay. Next, MuZero Alpha Zero suffers from bad initialization. I did experiments on Alpha Zero before. Very, very hard to learn. Very, very hard to learn. Let me emphasize that. So much weeks spent trying to get it to work. Yeah, so it's a great example of learning from future simulations and gaining back the experience. But if you have a bad value network, a bad policy network, or just give bad experiences to begin with and let it learn that, oh, maybe maybe doing this action is great, but actually it's horrible. It's very hard to unlearn the action if the with a bad initial configuration. That's why when Alpha Zero um like beat Licedo, it's not Alpha Zero, it's actually the one that is AlphaGo. Yep. It actually started with human best actions as the initial config. So So they have a sort of a neural network that is already like initialized at a certain point of state space that is not too bad, and you can shift it a little. Yeah, if you don't have that initial configuration, you try to use reinforcement learning to learn from a horrible starting state, can be very hard to learn. I have a friend in my NUS lab, like she she did some visual question answer, and she realized that if she just does supervised fine tuning, it did pretty well. Supervised fine tuning with like some variant of proximal policy optimization, like RL in general. Yeah, she used group group sequence policy optimization, GSPO. Yeah, it's like the advanced version of group relative policy optimization, GRPO. So basically, she realized that using RL together with the fine tuning is great, but if you just use the RL straight away, you start with the GSPO straight away, is worse than using the fine tuning. So a lot of these reinforcement learning methods, the initial configuration is important. If you have a horrible starting configuration, good luck. It's very hard to learn from just the environment rewards alone. Yeah. So in order to mitigate that in system M, like I think one of the best ways to do it is have many initial configurations. And one of the best ways to do that is to use population learning or like genetic algo, for example. Yeah, so that you mitigate the effects of having a horrible starting config. So maybe in the Alpha Zero case, instead of just starting with a random seed of 42, you start off with random seeds of from 1 to 1 million, run the algo and see which works best, select the best one, and maybe that can be the initial state for the next generation and so on. You could do Alpha Zero training with genetic algo. Yeah, you just need to choose the right weights to propagate to next generation. Yeah, so yeah, these are some of the things that I think what deep learning algorithms suffer, yeah, you can mitigate with more initial configs. Yeah. Anything to add? If not, I move to the next slide. Okay, it's a little late, so let's try to end in the next 5-10 minutes. So now the next part is group learning. How about group learning? Can we add group learning dynamics to this framework? The answer is yes. I think we should. Then we have discussed this already with the particle swarm optimization and genetic algo. Okay, same thing. Must everything be a loss function? Not necessary. We can do the same few algos that I talked about. Must everything be optimal? Okay, we also discussed about this. So I think we shouldn't chase optimality because it reduces diversity. We should instead have diversity and have a way to just select the right agents for the job so that we can keep more skills in the pool, in the population pool. Okay, so we can adapt better. Yeah, so this is my take on it. I do think the future of intelligence is a swarm intelligence because a group can do way more than what an individual can. It can adapt way faster as well. Yeah, if you just have an individual, you are limited to what that individual knows. But if you have a group, you have the knowledge of the whole group. Yeah. Like right now we're having this discussion, right? We each have our own life experiences and so on. If it's just me having a conversation with myself, yeah, sure, I can learn stuff by thinking about it myself, but it won't be as much as learning from a diverse group. So I do think that a diverse population is important and some way of information sharing is important as well. And you don't have to be the best, right? You just need to be good enough to survive in your environment. And that would encode diversity in the next generation. Yeah, so I think this is very important. Like we need to stop just pursuing the optimal. Like in order to adapt and do continual learning, you need to have diversity. Yeah. So just end off with this question. Any feedback, comments about today's session? Anything else you want to talk about? Maybe you have 5 minutes before we end.
If you sorry, yeah. So if you bring this back down to the most like let's call it the principles rule, right? First principles rule. The question is you have temporal and semantics, right? And then optimal for diversity or diversity. The question is you have to have diversity within semantics and temporal understanding, or we can call it knowledge base, right? Humans are different and creatures and everything like like our like not silicon matter, let's call it like carbon matter. We're a little bit different than agents. Like I don't want to compare us the same way because we have empathy. I don't know if agents have empathy, right? Like I don't know if they have that
I mean, you can encode
capability.
it in. Yeah.
Like I can't verify that, so it's hard for me to like get into this idea of diversity from an empathetic perspective, but from a perspective of like intelligence, right? Like true raw intelligence, you have to have semantics and temporal, right? Like timing is super important, understanding all of that, and then semantics is like context awareness. But like, at what level does diversity matter when you're trying to break it back down into the simplest core, right? Like principles instead of applying this philosophy of like life.
So you're saying that we don't do genetic algo? I mean, the philosophy of life is like natural selection and stuff.
I, I don't know. Like it's not what I'm saying. I'm saying that agents don't really have, or AI right now as a core, right, is just it's vectors, right? It's mathematics, and mathematics are not like diversity is one thing, but they're very deterministic. Math is math, right? It's
Oh,
either
okay, I get it. I get it. You're talking about the substrate of intelligence, right? Being vectors.
if we're going to be able to apply this level of intelligence that we've just talked about, we still have to be able like when somebody told me knowledge is power, I'm like no, it's not. Applied knowledge is power. So you can have all the knowledge in the world, but if you don't apply it, it's nothing. So we still have to figure out how to apply this paper or like everything that we've discussed in order to test to verify it. So I don't know about the diversity part because I see the value, I just don't know how to apply it from that perspective, at least.
Yeah. I think we don't have to constrain ourselves to vectors. I mean, vectors might be just the dominant era of how we encode the representational space and so on right now. But in order to get like a solution to a problem, just vectors can just be one approach. Yeah. So the way we do population learning is independent of the substrate of your intelligence. Like you can do it on rule-based learning as well. You can do it on I don't know, like other than vectors, maybe you could do uh, if else statements. I don't know. Yeah, so it's something that I think is independent of the building blocks of how you build the agent up. Yeah, you can still do your selection and your diversity from there. Yep.
Yeah, there was that one paper we covered. Do you remember, John? It was memory three, memory
Memory
cubed,
cube,
something like
yeah,
that.
memory cube, correct.
Memory cubed. I do really like that paper. It's a long story short for Robert. It's the paper was covering an architecture for memory for I believe agents. Like I believe it's a separate memory system, but it had three levels of memory. It was,
Yeah, it
I
was like the
believe,
weights and bias memory, and then there's another abstraction space, which is like the vector representation. And finally,
yes.
we have the the memory in the database, like your text and your images stored in some vector database. So you have an intermediate memory, which is like the vectors that you can straight away like put as your first few tokens without needing to convert the text into the vector space. So they have three different forms of memory, and you can learn from one another. Yeah, so quite interesting paper because it allows for like caching of intermediate states.
Yeah, and that was my point, is that the memory itself was transmutable. It wasn't contained to one single abstraction space or one single medium of information storage, like the parameter level or the database level, the text level. It had multiple levels of abstraction that you could utilize for different purposes or different environments, essentially. So the strength of the paper was, I wouldn't really call it multi-agent, but it kind of showed the advantage of having multiple levels to your architecture, right? That kind of diversity and allowing for the orchestration to occur and transmuting your information or your knowledge through multiple mediums, right? It could be multiple agents, multiple levels of abstraction, regardless of the implementation, but the core idea remained the same, that you could take the knowledge and the learnings from your environment over a lifetime and transmute them accordingly and adapt them. You weren't limited to one single medium or one single perspective, right? You don't have to encode all your information into vector space and hope you don't lose any useful information via the compression loss, right? You had ways around it. You had ways to implement and adapt.
Mm. Yeah, so there's different abstraction spaces, and you can adapt in each of them, right? That's what you're saying.
Yeah, this is yeah, that's my point. Is that the memory theory paper showed a implementation of how to get around certain issues with getting caught in one medium. Because I think Robert's is getting caught on the issue of vector space and how to implement these very high level ideas on our current paradigm, which is kind of removed from these higher level concepts. It's very vector based, very encoder block, and parameter based. You know what I mean? It's very
Yeah.
mathematical. Very
So,
mathematical. It's a
mhm.
lot of functions.
So I think even for the metas paper, you can also adapt based on the system M. You can adapt on the memory space. You can adapt on observation system A, action system B, and I would like to add on, you can also adapt based on the body as well, although it's not covered in this paper, like robotics, self-evolving robots, that kind of thing. You can create yourself a part that might be useful for grabbing, that's next level robotics. You can 3D print what you need. Yeah. So I think this is something that is very useful because you don't just want to stick to one abstraction space. It's very limited. Like if you just use only one abstraction space, like for example, your abstraction space is about let's say your abstraction space is about moving your finger up and down. You can only do very limited things with it. But if let's say you talk about more like abstraction space of your vision, hearing, like abstraction space of an individual, abstraction space of groups of people, like there's so many things you can model just by having different abstraction spaces here. And I think it's very important to know that intelligence is not limited to just one space. Yep. So I think that's a great point. Yeah, that's a great point.
Is it more important to know what to do instead of what not to do? Like physics is a unique like thing that we have to live with, right? Like as much as I want to be able to jump as high as I possibly can, right? Physics like constraints that. So I don't know which is more, if we're thinking about it from a metacognition, this paper basically is metacognition. It's the ability to like I mean self-evolve, really. It's really true autonomous intelligence. The question though I have is what is more important, to know what not to do or what to do?
I think you need to know both actually. Yeah. Because like in order to know what to do, you can perform them better next time. You learn what not to do so that you can avoid them. Yeah. I mean, They are just two
But
sides of the same coin, right? Like one is trying to get to something, one is trying to not to get to something. Yeah.
that's what then the optimization, it would be the opposite. Optimization would be trying to get something done. Diversity would be the opposite, would be both, wouldn't it, at the core?
You can also do both for optimization, right? Like because in order to get something done, maybe you need to avoid what not to do.
But how would you know what not to do if you don't just try? Because you don't optimize not what to do.
By optimizing for what to do,
Well,
you
we don't
you
optimize what not to do. We just go on with our lives. Right? Like if we were always optimizing it, we would like be probably living in spotless houses, but we don't optimize for our longevity. We don't optimize for anything. We just coexist, right? So like,
yeah. I think what you're thinking of is like what should be your priority in life? Like what should you focus on? Should you focus on doing things or should you focus on trying to not get into trouble, that kind of thing? I think this is something that is goal-directed learning. It really depends on what you want to do in your life. And this is something that I think in terms of optimization, it's probably not a great word to use for this kind of learning because you have so many objectives you want to do. Like how can you optimize for all of them? It's very difficult. And so it might be better off to
but
like,
in this
yeah.
paper right here, it says system B action slash policy. That would be optimization, in my opinion,
It is. It is. This whole paper
right?
is about optimization.
And system A, which is perception slash world, which would be almost what, like, I don't know where the what not to do comes in. Like, I think that's what's missing in this. Like, you
It's
kind of have.
probably system B. What not to do is given your goal, what action should you take? So it's a policy of what you should do. So whether you choose to do something or not to do something, it should be in system B. Because system B is where the action takes place.
Yeah, because your diversity concept to me in math doesn't make sense. But if you do it this way, it it's a like it's I just don't know which one to go for first, like where to go. Do you have to do them both at the same time? Like
You
as
don't have
humans,
to. You don't have to choose. So diversity means each individual will just optimize for their own individual goals, and only as a group, then we do the selection at the end of their life cycle.
Can I chime in here?
Yes,
Uh, like I think I agree with the point that you see you don't need to perfectly choose because like in your learning process, right, you will get both positive and negative feedback. And the negative feedback can, I mean you can use both more positive and negative to learn. Like one example is constructive learning. For constructive learning, you need both positive and negative examples.
yeah, good example. Yeah. So you push towards the positive examples being closer together, and you pull away for those examples that are negative. So in fact, for stuff like CLIP, contrastive language image pre-training, they also use contrastive learning to learn embeddings between image text pairs. Okay, because like similar pairs, you make the embedding to similar, not similar pairs, you push them away. So something like this, I kind of think you need both in order to learn, right? Because you cannot just learn only from the positive, right? Yeah, you still need some negative feedback. Yeah. Same thing for negative feedback. If you just learn from negative feedback, your agent might just end up doing nothing. Okay, because if you do nothing, you at least don't get any negative things other than wasting your life, I guess. Yeah, but yeah,
but
that's
then layers of abstract also apply too here, because if you think about it, right? One thing that I may do that may be negative, I don't really care. I constantly keep doing it. Let's say some people will get habits where they're bad habits, right? Some people get these like in their minds, like, well, like how do you prioritize? Because if you don't have prioritization in diversity, which we just think it's just naturally going to come out to be the highest level of intelligence, I don't think that's going to work. Like you like a bee is 100% the most optimized creature, right? Like if you look at, maybe if you look at humans, we're not that optimized, but other animals are, or other species are compared to us. And like if you think about like a dragonfly, it has a 98% accuracy of trajectory of killing a bug, right? So humans are very on product, like good that way. So I don't know if our answer is going to come from literally modeling after the human perception of intelligence, because
Mhm.
we're just like one form of intelligence. So it's like, how do we optimize and understand like that aspect. Like, can we just go along with our world's trusting, or do we actually at one point need to verify in order to actually have true intelligence? Like, it's a hard understanding of what really, like, should I just trust you because you say, oh, like, Robert, this is, going down these stairs is dangerous, and I never want to go down the stairs, you
You
know?
won't know unless you try it out, right? But the thing is, do you want to try it out? Yeah, if someone tells you going down the stairs is dangerous, maybe you can go down and you never come up. Yeah, so the thing is it worth risking the negative gains just to find out more information and verify it? Sometimes you may not need to verify it. Like if you can live your life
That
without verifying it, then that's good enough. Yeah.
that's the most interesting, because remember, with like a planes, right? The Wright brothers, somebody had to take it. Everybody said, "Oh, that'll never work. That'll never work," right? And then they built a plane, and now we go everywhere in the world through planes. So
Yeah.
the risk
You
for
see,
learning is
let, let
more
me let,
important than constrative, I think.
let me just share
Risk,
with you this example, all right? So I like your point a lot. And you see, you don't have to take the risk as an individual. You're individual, you don't have to take that risk because you are constrained by certain memories and stuff like that. You may not choose to take that risk because it doesn't make sense for you. But someone new in the world who has never heard of such negative stuff is like, huh? Isn't it flying is very normal? Let's try to build a plane. So that person is willing to take the risk because in his memory, in his life, there's no risk at all. It's not a risk. It's like, why are people not trying it? Let's try it. Yeah, so that's why I say we need evolution because you see, even in research space, right? People who have spent their lives doing a particular algorithm, they might be just focused on that algorithm, say deep learning. Everything must be a loss function. But it takes people who have different perspective to combine them, to go different routes. And they might find out new things, but you cannot do that with the original people who invented it because they might be too stuck on that point of view. So I'm saying that you can still take the risk, you can still do stuff, but you don't have to do it at an individual level. Like that individual may be stuck there, no problem. But because you are doing a group kind of learning, other individuals might be not stuck. And then these individuals advance the population. And that's why group learning is important. You cannot just have one agent. It's very easy to get stuck with one agent. Yeah, do you see the point here?
yeah, I totally see the point, and I think, the more and more I think about it, because if you're passing on, okay, like, let's just, I always like to break them down to the simplest steps. Like, if I see somebody, I'm afraid of going somewhere, like say up the sketchy ladder, right? But I see somebody do it, I'm absolutely going to say to myself, okay, well, they did it, so I can do it, and not a big deal, right? Like, exactly that same way. But the question is, are they passing on that knowledge to me in a way that I have the ability to do it, or am I doing it through some level of like non thought? It's almost like it doesn't come down to an intelligence aspect there. It's a transfer of something, but it's not intelligence. And what the question is that a fear? Like, is that what's motivating us or not motivating us? Like,
Yeah.
it's interesting to decide where the future of intelligence is. Maybe intelligence is not actually comprehension, right? Or cognitive, metacognitive. It's about um, wisdom, right? Like, basically me learning from you, but either by, we can call it abstracts, like learning visually, right? Learning through body, learning through all of these different layers. But the problem is, um, we still do need to optimize, or we constantly don't succeed. Like, at the end of the day, how do we get better? Like a plane, like Elon Musk is one of the greatest people in the world when it comes to, like, why he's a trillionaire, is because he is a master of optimization. He goes through his model is, and like, how can we just lose 1 pound a day of this vehicle? How can we save $1 a day?
Yeah, see,
Right?
this is not exactly optimization. It's like going towards the optimal, but it may not be the optimal. Like, so even Elon Musk cars, they may not be the most optimally designed cars. They're just heading one step towards there, and that's good enough. So in our daily lives, we don't have to be like, oh, I want to be a chess master, and then next day you are a grandmaster. No, it doesn't work that way. You go slowly, step by step, and that's enough because you know that you're heading towards there. And like, if let's say you were to say that I will only do things if it's optimal, you'll probably never do anything, right? Because
True.
it's hard to be optimal. Yeah, in fact, in the real world, what do you even define as optimal? Because the world is always changing. What was optimal 1 second ago may not be optimal the next second. So
So
is it,
what's the
yeah,
goalpost?
say again?
What is the goalpost? What's the goalpost? So if it's not optimal, what is the goalpost? Because we are constantly evolving to get better. Like, I mean, right now we're talking about AGI, right? We're talking about these concepts of super intelligence. We're talking about these, ideologies that are defining our characteristics of intelligence, right? And what we think of it. Used to be, information regurgitation, right? Or like the ability to have a memory to share what you know and is good. But now today you have to be able to obviously reason and be able to actually apply it. So is the intelligence layer application again back to action, or is it simulation? Because it's such a different aspect. Like it really is harder to understand, because if we can simulate intelligence, right, then we can predict the future in theory. But if is prediction of the future a temporal issue, which allows us to get basically, I mean, that's where it gets really, really scary, is because, and that's like string theory, quantum, and all of that stuff. But basically, it comes back down to the idea is that if it's not optimization and it's not diversity, the goalpost has to be like almost prediction of uncertainty, if that makes sense. Like, really,
I
I don't know
mean,
how.
you can do both. You can do prediction of uncertainty. You can do prediction of future states. You can do optimization or other satisficing methods. I mean, you can do both. You don't have to limit yourself to one. Like system A and system B are just like that. System A is about prediction, and system B is about, I guess, optimization. Yeah, I mean, both are optimization in some sense, because to do prediction, you also optimize your prediction. Yeah. So I think you do both. Then for simulation is a whole new level above that, because to simulate you need your world model. So I think only some organisms do simulation, like animals, mammals, and birds. The rest of the species, they don't really simulate, or at least we don't think they do. Yeah. So evolution has different ways of intelligence, and there's no fixed way. And I think it's a combination of everything really that defines us. But we also don't need to mimic humans to do true intelligence. Like, what even is true intelligence? What even is general intelligence?
Well,
There's no, yeah.
that's where intelligence is interpersonal, but we're also missing out one of the most important aspect, which is environmental intelligence, right? So the idea is like, sometimes people, they call, like I said, clairvoyance, they call these like different concepts of, right, where we can tap into these sources. People call them flow states, they call them other things, that, right, or they call them savants, whatever you want to call these things, right, that they tap into this universal understanding of intelligence. So it's like, really, and I keep coming back down to, is this prediction? Because if you think about it, right, instead of optimization, if you think about it, if we had to do a simple race, right, and you had to go from start A to start Z to the finish line, and you had to run every single thing and cross, but if I could be at every spot at every place at the same time, when the race starts, I've already won.
Yeah.
Right. That's how quantum works. So it's like, as we say, is quantum optimization, like, whether we like it or not, right now, quantum computing is going to change everything we're looking at right now. So whether we are the highest level of intelligence today, we still have to take into consideration that maybe intelligence is like you said, swarm intelligence by far.
Yeah, I like your definition of your quantum being like in every place at one, means you win the race regardless of where the race ends. Yeah, I think that's great, because that's exactly swarm intelligence. Regardless of where the environment leads you, you should have a few surviving people or like fit people. Yeah, that's a great. Yeah.
Nice.
Well, anyway, I think we should probably end now.
Yeah.
We have a great discussion, but I think it's quite late already. And just to sum up, this paper is really quite interesting. It talks about system A, the learning from observation, system B, learning from actions, combines them with a meta controller, and then evolves over generations. All these are still in the framework phase, and I think it's very interesting thing to learn over time, and we should incorporate more of the group learning ones, because I do think it works better than deep learning in some instances. And yeah, I think next week we can talk more about a book that I've been reading. It's called Brief History of Intelligence by Max Bennett. Talks about how intelligence evolves over time, from worms all the way to animals with simulation and so on. And I mean, it starts with reinforcement learning, then simulation. So I think this is a great follow-up to this paper. Yeah. So yeah, thanks for coming, and I'll see you all next week then. Okay. Bye.